Section 5.1, page 3. So we were talking about the area under a curve, and now let's go for the formal definition. The area for some region R that lies underneath the graph or the curve for a continuous function is the limit of the sum of the areas. So we've only talked about the sum of the areas, but let's look at this a little bit closer. So we already looked at the Greek uppercase letter S for summation, for subscript I equals 1 up to some set of rectangles n, where this is the formula for our curve, or f of x is really. And we're going to multiply length times width, or maybe you're more familiar with saying height times width. Width is how wide each of our rectangles are, which is constant, but the height of our rectangles kind of depends on each different rectangle. And so we were adding those up, and we said this is approximately the area, and as we saw, it wasn't exact. Well, it turns out if you took this formula, and you took the limit as n goes to infinity, meaning you have infinite number of rectangles, then it is exactly the area. So let's put some of this terminology into a tangible visual. So n, remember, is going to be our number of rectangles. Perhaps you're going to determine that, perhaps you will be told. And as we just said, the more rectangles, the better, which is why n goes to infinity, but not feasible for us to find. Delta x is the width of each rectangle, and we determine it by finding what is the range of the curve we're looking at and how many rectangles do we want. This is where A and B will be the endpoints of the entire interval. Next, we have x sub I, and it states this is the partition of the points, but it kind of helps us see where each rectangle ends, and that's where A plus I delta x, this is actually walking you to each next iteration. We've already discussed L sub n for left endpoint rectangles, R sub n, whatever number n is, for right endpoint rectangles, and M sub n for our midpoint. Now, we hadn't discussed two other options that you're going to see visually in a moment, which is upper sum, and basically for each column we look to see where the graph it's touching that column at the highest point and use that to determine whether it's going to be a left or a right rectangle, and so you can have a combination. Same thing with lower sum. We're going to look to see where the column crosses the graph and go with the lowest y value. Now notice we're not going to call this L sub n because we already have L sub n. So example 3 says identify the following approximations if they are left, right, midpoint, upper, or lower. So keep in mind the graph was originally given with these green rectangles and just this red line. So what I did is I looked at this first rectangle, and I can see that the graph touched below the rectangle and up here on the right side of the rectangle. Now I'm going to look at this next rectangle. Now the graph touched the rectangle, the upper and lower, but if I went across the lower, it's not the top of my rectangle. But if I went across the upper, it is the top of my rectangle. So it was this right side of the rectangle, and I can see that there's 1, 2, 3, 4 rectangles where when I isolate a single rectangle and draw lines where it crosses the graph, it's the point where the graph is crossed on the right side that created my rectangles, so I have R4. This is that whole upper-lower problem we've just discussed. I'm looking at just this first rectangle. Now, if where the graph crosses this column, right, pretend there was no pink or blue, if I go across at the upper point, I'm at blue. But if I go across at the lower point, I'm at pink. Let's see if that stays consistent. The upper point gives me blue, the lower point gives me pink. So I have upper sums in blue, whereas pink is my lower sums. Now notice it could switch off as to whether it's kind of a left or a right rectangle. This very first column, the lowest point is a pink that's a right side of the rectangle, but over here, column 7, it's the left side that gave me the pink. The bottom line is it was the lower of the two signs, and that's why we refer to pink as lower. And we usually just say n equals 9. I didn't actually write it on this one, but since we don't use subscripts. Next graph, I've got these blue rectangles and a dark blue curve. So I isolated my first rectangle. When I used the graph at the edges, going across the bottom edge didn't help. The top edge did. So I'm either thinking this is going to be left sum or upper sum. I'm not sure yet. I come to the next piece. Still left and upper. Come over here. This is left. Oh, that would have been upper. So it's not an upper sum. It was a left. I got to a point where the left determined the top of my rectangle. And so originally it could have gone either way, but it didn't. And again, it's easy enough to just count how many rectangles you have. Next one, I've obviously got the answer, but let's assume we didn't. Now, obviously the dashed lines help, but also I would have seen where it crossed, right? So if I was just looking, let's say at this middle column, my graph crossed here. That's not the top of my rectangle. My graph crossed here. That's not the top of the rectangle. The top of the rectangle, oh, it's dead center in the middle of this column. And again, there were 6 columns. Okay, so in example 3, you were given the rectangles and had to determine whether it was, right, left, midpoint, or upper lower sum. Example 4 didn't have any of these rectangles when I started this problem, but I filled them in. So here, I'm asked to draw the rectangles and approximate the interval from -2 to 3. And so I would be given either L5, lower sum, N is 5, or M5. Now, because these are all 5, that is my N value. And the formula for delta X, the width of my rectangles, is where does it end minus where did it start. We're trying to find the range. And so we're going 5 units across, and because we want 5 rectangles, each rectangle will have to be width 1. So on this first example, I would have only had this blue graph that I just highlighted. And I would have seen my -2 and my 3. And so I would have drawn a column 1, 2, 3, 4, so that I can have my 5 1-unit width rectangles. But you'll notice when I drew this, I made this kind of dashed column to define the first rectangle. I didn't know where the top of my rectangle was. But because it says L5, I would take this rectangle and I would come to where does the curve cross on the left side and go straight across. My next column, the graph crosses twice, but on the left side, if I go across, I'm able to create all of these rectangles. And that's really all that happens. Now, here's where I feel it could feel a little odd. These are left-sided rectangles. So what do? You put a dot on the left, but then you move to the right to close off the column. And so left rectangles start at the left and then move to the right. And I think that could be, confusing, but maybe just start with, I'm here, I've got to get to the edge of my column and just worry about headed in whichever direction gives you your edge. Exact same curve, but this time I was asked to do lower sum, and N is 5. We've already made my dashed columns, and for some reason this time I erased where they ended. But basically, I'm going to have to compare both the left and the right side to determine where the graph is crossed at the lower point, and then I'm going to move left or right. I don't know. So when I take this first column and the graph hits here and here, This one is lower, so I had to move from left to right. But when I look at this next column, where the graph hits up high on the left and lower on the left, now I'm going to go from, I guess this is my right to my left. So I'm looking at each column individually and where was the lower piece. Now this one's a little bit tricky because the lowest piece was actually in the middle. That can happen. It doesn't have to be left or right. So here's left, here's right, but it's where is the column crossed? And so in this case, because the curve kept going down, there was actually a point that was even lower. Watch out for that one. But in this case, I mean, you could have thought of your midpoint, but I'm doing lowers, right? So even if I had been thinking of midpoints all along, I got lucky up until that individual moment. The midpoint had always been somewhere not as an extreme. And then the last one to look at is M5, the midpoints. So I've got that exact same curve. I know that my first column goes between -2 and -1. So I just focus on these two column lines. I look to the middle of the column. I don't have to decide which is higher or lower. I'm told to go to the middle, and I go across. This next column, I come up to the middle and I hit my graph, and I just go across within the columns. Go up to the middle and across. So you can see a lot of various ways that our rectangles can occur.